Welcome everyone. Today I will give a talk about my project, Fine-Tune Large Language Model for Chain Source Reasoning in Code Generalization. In this talk, I will introduce the framework of fine-tune large language models such as Code Lemma to generate a code solution for programming while incorporate algorithmic reasoning. The purpose of this framework is to produce a model that not only generates correct code, but also provide detailed reasoning and validate the correctness of code using real-time feedback. Our main focus is twofold. The first one is chain source fine-tune. The second one is reinforcement learning with API feedback. This combination of fine-tune and API-based feedback will allow the model to improve its reasoning capability and generate code that is not only correct in style, but also functional correct, as verified by real-world test case. Here is the overview of this talk. At first, I will introduce the background. After that, I will introduce the learning object and the challenging. Then in the third part, I will introduce dataset and the model description. And as followed is the most important part of the talk is the training framework. And after that, I will talk about our evaluation metric, evaluation dataset, and the baseline. And then is the last part is the summation. Here is the background. Even if we can see from the table, even if there is plenty of research focused on training large language model to solving coding problems such as star code, code llama, wizard code. However, we can see from table that based on recent research, we may find that this code large language model don't perform well on lit code problem, especially for those lit code problem published after Jan 1st, 2023. So here bring us a research problem: how to train large language model to gain algorithmic thinking and can be applied to solve interview-level algorithm problems. To solve this problem, we propose a lower learning framework to fine-tune large language model. In our task, our goal is to fine-tune the model using a dataset including reasoning and solutions. After supervised fine-tune, we will use reinforcement learning to further refine the model using feedback from the API. We can say that in our task, we have three specific objectives. The objective one is to ensure the model accurately selects the algorithm to solve each problem. And then for the objective two, we want to improve the model ability to generate a chain sort. We want the chain sort can explain how the algorithm was chosen and how the solution was derived. Then for the objective three, we want to refine the code generation process so that the code can pass test case generated by LeetCode. And we will use LeetCode API to do such step. We can say that this objective highlights the focus of our framework, teaching the model to think and explain, and ensuring that the solution works in practice. Okay, after taking about the objections, I will introduce the challenger. The code challenge we are addressing involve training the model to not only provide reasoning for how the solution was driven, but also generate correct code. This can be taken as two main challenges. The first can be addressed by chain-of-thought reasoning. The model needs to generate step-by-step reasoning, making its thought process economically and interpretable. The reasoning should explain why a particular algorithm is chosen for a given problem and how the solution was derived. But we might find that even if the reasoning is sound, the generative code may not be correct. So here comes to the second challenge: how to ensure the code can be applied in practice. We think this challenge can be addressed by code verification, like LeetCode API. To ensure the correctness, we will introduce a verification stage using LeetCode API. We will run the generating code against a set of test cases and return a binary reward. The model will receive reward only if the code passes all test cases. Otherwise, it gains 0 reward. Then let's start by introducing the structure of the dataset. Okay, the dataset will be used for both the supervised fine-tune stage and the reinforcement learning stage. Our dataset contains more than 10,000 examples. Each of these examples is designed to include the coding problem, the correct algorithm, the reasoning why the algorithm works, and the solution. Here is a template of one example in the dataset. We can see that each example in the dataset is structured as X, Z, E, Y. And for X is the coding problem. Z is the algorithm used to solve the problem, such as binary search, dynamic programming. And E is the chain-of-thought reasoning that explains why the algorithm Z was chosen and how the code solution was developed. And for the Y is the final code solution that solves the problem. Then, okay, let's take an example. For the coding problem X, the coding problem will be described in natural language, such as searching for an element in a sorted list. So for this coding problem, the model must select the algorithm that solves the problem. For example, in this problem, algorithm Z will be binary search. Then for the chain-of-thought reasoning E, the chain-of-thought reasoning E is where the model explains its thought process. For example, in this example, it might describe the binary search it's used because it reduces the searching space in half at each step, leading to an efficient solution in time complexity. Finally, the model must generate the code that implements the algorithm and solve the problem. This is the solution Y. Here you may have a problem, that is why we need the chain of thought. Okay, let me explain it. The chain of thought reasoning is important because it has some advantages. The first advantage is that it can enhance interpretability. Chain of thought make a model's decision-making process transparent by explaining each step. The second advantage is that chain of thought can improve accuracy. By reasoning through the problem, the model is likely to make errors in its final solution. And the third advantage is chain of thought can enable debugging. If the final solution is incorrect, having a chain of thought allows us to identify where the model went wrong. Then we can learn another way to fine-tune the model and fix this bug. And then we can run to our model. In this project, we will going to fine-tune CodeLlama. We chose CodeLlama because CodeLlama is a transformer-based large language model, and it is trained on Coder and natural language. It has been pre-trained on plenty of programming language and tasks. So this making CodeLlama is a stronger candidate for both reasoning and code generation tasks. So in this task, we will apply CodeLlama to realize sequentially generation of reasoning and code. The model will be trained to predict algorithm, generate chain of thought, and generate code solution. Especially given the example X, the model will first predict the algorithm Z to be used. Once the algorithm Z is chosen, the model generates an explanation E, reasoning through the problem and explain why the chosen algorithm is appropriate. Finally, the model generates the code solution Y that implements the algorithm and solves the problem. Before introducing the detail of supervised fine-tune and reinforcement learning, let me introduce the overall two-step training approach we are used for this framework. This method makes use of the strengths of both supervised learning and reinforcement learning to train the model. We want the model can not only generate correct solution, but also produce intermediate reasoning step. We also want to verify its correctness of this solution using a real-world API to ensure the code generated can be used to solve real-world problems. So here you may have a question that is why we need a two-step approach, why we use one-step training such as supervised fine-tune. We use okay, let me explain. We use a two-step approach because solving coding problem with reasoning and code correctness involve multiple layers of complexity. First, the model needs to learn how to generate reasoning outputs, include both the solution to coding problem and a coherent explanation of how the solution is derived. However, even if the model's reasoning appears sound, the code it generates may not always be correct. Therefore, after generating the reasoning and the code, we need a way to verify the functional correctness of the generative code. This is why we need the LeetCode API to validate the code against test case. Use LeetCode API validates the code, providing feedback on whether the solution passed or failed. To handle these two different tasks, we break the training process into two steps. In the first stage of training, we use supervised fine-tune. During this stage, the model is trained using a labeled dataset where the correct algorithm, reasoning, and solution are provided. The goal of this stage is to train the model to perform well on this task using supervised learning technique. We will go into detail of this step shortly. After supervised fine-tune, the second stage of training involves reinforcement learning. which focus on improving the correctness of the generated code. In this stage, the LeetCode API will provide the feedback as a form of real-world evaluation for the code generated by the model. Here is how the reinforcement learning stage works. Once the model generates code, the code is evaluated by an LeetCode API. The LeetCode API will run the code against the test case. The LeetCode API provides a reward based on whether the code passes all test cases. Using this reward feedback, we can take advantage of reinforcement learning to further optimize the model's ability and generate solutions that pass the test case. In this way, we can maximize the likelihood of producing correct code. By combining these two steps, we can achieve the model can think before code and check after code. In this way, the model is trained to explain how it solves the problem through chain of thought reasoning, and the model is also trained to generate code solution that's also only correct in style, but also functional correct verified by LeetCode API. So in this way, we can guarantee that our two-step approach is effective because the chain of thought fine-tune can improve the interpretability. This step ensures that the model can produce structured and explainable output, making its decision process transparent and unstable and understandable. And the second reinforcement learning stage with API feedback can ensure the code accuracy. The second step improves the model ability to generate accuracy and executable code, ensuring that the generative solutions are validated against the real-world test case and can be applied to in practice. By separating the training step into two stages, one focuses on reasoning and code generation, and the other focuses on verifying and refining correctness, we can ensure that the model not only reasons correct, but also produces reliable solutions. Okay, then let's go to the supervised fine-tune stage. In this stage, we perform supervised fine-tune on the dataset, teaching the model to generate reasoning and solution based on input. The problem description X. The goal for the model is to generate correct reasoning and solution for each problem. And then, okay, let me introduce the training object for the chain of thought fine-tune. The objective during fine-tune is to minimize the following loss: LF equal to llama y times ly add llama e times le add llama z times lz. Okay, then let me explain the equation step by step. The llama y, llama z, llama e are weights that control the importance of the algorithm reasoning and the solution component. It is a hyperparameter. And for the llama y is the cross-entropy loss for generated code solution. This loss measures the accuracy of the generative code solution. And then for the LE is a token level cross-entropy loss for generative reasoning. This loss ensures that the model generates coherent and accurate reasoning. And then it is llama, and then it's loss z. Loss z is the cross-entropy loss for predicting the correct algorithm. This loss measures how well the model practices the correct algorithm Z for each problem. By minimizing this composite loss, we train the model to generate both reasoning and correct code solution in a structured manner. Okay, after we finish introduce the supervised fine-tune stage, let me introduce the reinforcement learning stage. We introduce reinforcement learning stage to incorporate LeetCode API feedback into the training process. The goal here is to use feedback from LeetCode API to refine the model's ability to generate a code that passes real test case. While the model learns to generate reason and code during fine-tune, we cannot guarantee that the generated code is functional correct without running it. This is where the LeetCode API comes in. The LeetCode API runs the code and checks whether it passes all test cases, return either 1 if the code passes all test cases, or 0 if the code fails 1 or more test cases. Reinforcement learning allows us to refine the model's ability to generate correct code based on the binary feedback. We will use a policy gradient approach to maximize its expected reward for generating correct solution. The reinforcement learning loss function is designed to maximize the probability of generating solutions that pass the API test case. Then, after got the reinforcement loss and the supervised fine-tune loss, we can gain the total loss. That is the summation of both of them. Then we aim to minimize the total loss. And then let's go to the next part, the evaluation. Okay, so in the evaluation part, for evaluation purpose, we will use algorithm accuracy rate and code pass rate. For the algorithm accuracy rate, this matrix track how good the model can correctly predict the algorithm Z used to solve each problem. And the code pass rate evaluates how good the generative solution passes the API test case. Compared to the algorithm accuracy rate, in my opinion, I think the code pass rate it is much more important because it evaluates whether the code generated is good. Is good and can be applied to real-world application without human debugging. And then after introducing the evaluation matrix, I will introduce the evaluation dataset. For the evaluation dataset, we will use the LeetCode problem released after June 1st, 2023. Here, I needed to mention that even all of our training dataset is also from the LeetCode, but all the problems conducted in the training dataset is published before June 1st, 2023. So there is no overlap between training dataset and evaluation dataset. And then it is the baseline. As mentioned at the beginning of the talk, there are a lot of large language model have been proposed to solve coding problem. So we will select this good code large language model as baseline, such as star code, llama, wizard code, and other previous code large language model. And we will also report the code pass rate. And finally, it is the summarized part. In this presentation, we discuss a comprehensive framework for fine-tune large language model like CodeNumber to generate reasoning and code solution for coding problem. With caring more about the functional correctness. This is the major difference between previous work. So here is the 2 key points of our framework. The first framework is chain of thought fine-tune. We fine-tune the model using a dataset more than 10,000 examples to generate both reasoning and solution. And the second key point in this framework is reinforcement learning with LeetCode API feedback. We introduce LeetCode API feedback to ensure that the generative code is functional correct. And we use reinforcement learning to refine the model ability to generate code that pass all test cases. So thanks for listening. Here is all my talk today. Thank you. Oh.